Have you ever wondered why earthquakes happen, why volcanoes erupt, or how mountains form? The answer lies deep beneath our feet, inside the layers of the earth. Today, we'll explore thermal convection and how it moves tectonic plates, the properties of Earth's layers that drives this process, and how these forces shape the world around us. By the end of this lesson, we'll be able to model and explain the process of mantle convection and plate tectonics. Let's get started. In order to understand plate tectonics, we first need to understand the Earth's structure. Earth is made up of several layers, each with unique temperature, density, and composition. Inner core, the hottest layer, that is about 5,200 degrees Celsius, solid due to extreme pressure, made of iron and nickel. Outer core, a liquid layer of molten metal that generates Earth's magnetic field. Mantle, the thickest layer made of semi-solid rock that flows slowly. This is where thermal convection occurs. A stenosphere, a part of the upper mantle that behaves like plastic, allowing tectonic plates to move. Lithosphere, the rigid outer layer made of crust and upper mantle broken into tectonic plates. As we move deeper into the Earth, both temperature and density increase, and this temperature difference is key to plate movement. But what causes these plates to move? The answer is thermal convection, a cycle driven by heat from deep inside Earth. The heat comes from two main sources. One, radioactive decay. This means the breakdown of elements like uranium in the mantle and crust that generates heat. Two, leftover heat from the Earth's formation. This means heat from when the Earth was first formed is still trapped inside. Here is how convection works. 1. The mantle rock near the core rises because it's less dense. As it rises, it cools and becomes denser. The cooled rock sinks back down, creating a convection current. These convection currents drag tectonic plates along like a conveyor belt. This slow but powerful cycle is what reshaped Earth's surface. Tectonic plates don't just float randomly. They move in three main ways, all driven by mantle convection. In divergent boundaries, plates move apart where convection currents rise, creating new crust. Example, Mid-Atlantic Ridge. In convergent boundary, plates move together where the convection currents sink, forming mountains, volcanoes, or deep-sea trenches. Example, Himalayas and Mariana Trench. In transform boundaries, plates slide past each other, causing earthquakes. An example is in San Andreas Fault. Each type of plate movement creates different geological features. Let's zoom in on a convection cell to see how plates move. Rising mantle rock at the center pushes plates apart. Cooling rock sinks on either side, pulling plates downward. This continuous cycle drives Earth's tectonic activity. Without convection cells, Earth's surface would be static. This means there would be no earthquakes, volcanoes, or mountain building. Now, let's review what we have learned. Earth's layers have different temperatures and densities affecting movement. Radioactive decay generates heat, driving thermal convection in the mantle. Convection currents move tectonic plates, creating earthquakes, volcanoes, and mountains. Divergent, convergent, and transform boundaries each shape Earth differently. Think about this. How would the Earth's surface look like if the mantle convection stopped? Let's discuss.